So this is APC recording number 4. It's going to cover conductors, capacitors, and dielectrics. And we're actually going to go through all 3 of those in this one video. Excuse me. So conductors. If we're talking about electrostatics with conductors, here are some things you need to know about them. The electric field is 0 everywhere inside the conductor, whether it is solid or hollow. And that's because if you were to place a test charge somewhere inside that conductor, because conductors contain mobile electrons, the electrons in the conductor would move instead of the test charge actually experiencing a force. If the conductor is isolated and carries a charge, the charge resides on its surface. That is because all of the charges do not like to be near each other, and they will spread out as far away from each other as they possibly can. The electric field at a point just outside a charged conductor is perpendicular to the surface of the conductor and has a magnitude of sigma over E naught, where sigma is the surface charge density, so it's related to how much surface charge is at that point. And again, for something that's irregularly shaped, you will have more charge density at places with smaller radius, where you have corners and things like that. So let's see if there's a diagram. Yes, well, here, can y'all see that the charge is aligned here at the outside of this surface? But notice the charge density is a lot greater here where you've got a smaller radius turn. Same thing here. And the electric field lines are also more concentrated as a result. I definitely want you to know this. So this relates the electric field and the electric potential inside a conductor. There is no electric field inside a conductor. We just said that because a test charge would not experience a force. Instead, the mobile electrons of the conductor itself would move. But that does not mean that there is no potential inside the conductor or throughout the conductor. There will be the same potential at every point in that conductor. But electric field, remember, is a measure of the rate of change of the potential per unit distance. And so, in other words, E is dV dx, if you're better that way. So we may have a potential value, but because it's not changing, the electric field is 0. Same thing here. Electric field then is kq over r, so it decreases steadily as we move farther outside the radius of this conductor, and more exponentially here for electric field because it's kq over r squared. So you've got that 1 over r squared relationship here, and this is just an inverse relationship there. For 2 conductors, if these 2 conductors are at the same potential, notice they've got a wire connecting them, so the potential would have moved from point of lowest to the point of lowest potential. And for that reason, we know that they are at the same potential. This sphere has the same potential, but it will have, since it has a larger radius, it will have a smaller electric field. Again, because there's the same potential there, so the electric field, there's an inverse relationship there. If you have a smaller radius, you have a greater electric field. And that's a 1-to-1 relationship. Let's see. Oh, there it is. E1 to E2, when you work it all out, comes out to R2 over R1. So that's an inverse relationship between the radius and the electric field if 2 spheres have the same potential, or if 2 conductors have the same potential. All right, so this is talking about electric field and electric potential. Again, that's what I just said about the potential may not be 0. But I do want you to know what Faraday's cage is. A Faraday's cage is basically an enclosed metal or an enclosed conducting surface. It has to be entirely enclosed, including like the floor. And with a Faraday's cage, there will be no electric field inside that cage. There still may be a potential, but no change of potential. This is just showing you that even from here, from point 3 to point 4, right there, inside this conductor, there's no electric field. Inside this conductor, there's no electric field. There is an electric field running from A to B. And this is defining it. those. Actually, I recommend y'all go through and you look at this example. Let's go through it. So if we put a Gaussian surface inside 1 and it's uniformly charged, then E1 is KQ R over A cubed, and that's like if it's small because it's uniform. A is less than R is less than B. R, where's R? Not sure. What I really want y'all to see is 2 at point 2. You do have an electric field right here. It's KQ over R squared. At point 3, you don't have one at all because using a Gaussian surface at point 3, the total charge inside is 0 because you've got positive Q here and you've got negative Q lined up here on this surface. And so if you put a Gaussian surface right there between the edges of this conductor, you would have 0 inside charge, so there's 0 electric field there. And then for the total charge inside a sphere out here would just be Q, because it's Q plus, I'm sorry, negative Q, so Q plus negative 2Q is negative Q. So the electric field is negative KQ over R squared. And those electric field lines would be drawn just that way. I think that's it for conductors. Next, capacitance. So capacitance is a ratio of the charge to the difference of voltage between 2 points, between 2 conductors. It is always positive, and it is a capacitance. Like if I have, y'all have heard of heat capacity or something like that. It is a capacity. It's how much charge can be held between these 2 plates if a difference of voltage is developed there. To understand capacitance, think of similar uses of the word. The capacity of a milk carton is the volume of milk it can have. The heat capacity is the amount of energy it can store per unit temperature. The capacitance of a capacitor is the amount of charge the capacitor can store per unit of potential difference. It is a ratio of charge to voltage difference. So look here. A capacitor stores a charge Q at a potential difference of delta V. What happens to the voltage applied to the capacitor is doubled to 2V. The correct answer is that the capacitance remains the same and the charge doubles, because the capacitance is just a ratio of how much charge can be held with a particular change of voltage. That is correct. To calculate capacitance, we use Q over delta V, or we can use E naught A over D, and that's best for 2 parallel plate capacitors. We're going to go through the cylindrical capacitor and the spherical capacitor in just a minute. I will come back to those. All right, equivalent capacitor for a series or parallel circuit. If you have 2 capacitors that are placed in parallel, we know that if current's coming out of the battery, coming out of the cathode, then it can split and go down either path. But that means that the total charge that was coming out here, some of it went here and some of it went here. We also know that the difference of voltage across each of the parallel paths is the same. And so if you do all that stuff, you get that the equivalent capacitance is basically the first one plus the second one plus the third one. Because those charges, the total charge is charge 1 plus charge 2. This is a rearranging of capacitance formula, which means C1, V, and these V's are the same. So if you connect capacitors in parallel, you just add their total value. If you connect capacitors in series, guess what you do? It's the inverse relationship thing. It's that 1 over CQ is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And that is because you are going to develop the same amount of charge. You've got a positive charge here and a negative charge here, and the charge is going to collect here, positive, and an equal amount will collect here, negative, and an equal amount will collect there, positive, equal amount there, negative. And you can have a different change of voltage across each one depending on what the capacitance is, remember, because that capacitance tells you how much voltage, what the relationship is between the charge and the voltage. But just like you would have constant current for a series circuit with resistors, let me say that again. That was not working. Just like you would have constant current through a series circuit with two resistors, you will have constant charge develop on each capacitor that's placed in series. There we go. And as a result, the capacitance, when you work it all out and you rearrange the formulas and you play with it a little bit, comes out to this. 1 over CQ is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So the formulas for equivalent capacitance are exactly the opposite for the formulas for equivalent resistance. The energy stored in a capacitor is 1/2 CV squared. Again, if you're graphing voltage versus charge, you get this line. And we know that potential energy is the area under the curve there. So, and I think I'm going to go through parallel capacitors, parallel plate capacitors, cylindrical capacitors, and spherical capacitors in just a minute in the next video.